Hello everybody again. Welcome back from lunch. And now we have the session on compilation frameworks. And we are starting with the talk by Max on equality saturation and joins.
Right. All right. Thank you, Amir. Yeah, so I'm going to be talking about a couple different topics today. It's going to be a bit of a whirlwind tour, so I encourage you to talk to me afterwards if any of these sparked your interest, because this is going to be surface level at best, given the time I have. All right, so I'd like to ideally make it through all three of these topics. We'll see how it goes. A lot of the work that I have been working on recently centers around E-graphs, which is a data structure, and equality saturation, which is a technique for program optimization that, as I believe the next talk will sort of focus on, has been used for sparse optimization as well as other sort of compilation and program synthesis contexts. So I'm going to give a quick whirlwind tour on that and actually sort of leave the application to sparse context to the next talk, because I think they're going to do a better job than I'm going to do. But then I want to move on to how recently we've been focusing on using relational techniques to basically power this compilation technique of equality saturation. And sort of branching off from there, another sort of angle on this recent work that actually came out of our sort of trying to imbue equality saturation with this relational perspective is an entirely new family of join algorithms, which we recently developed that we tested again in the relational setting, sort of applied it against DuckDB and things like that, but I think could see applications in the sparse context as well. All right, so let's get started. So if you haven't seen E-graphs before, this is an E-graph. This is your sort of baby's first E-graph on the left here. It looks very similar to an AST. This is, in fact, a very boring E-graph. And that's because we've partitioned it into two parts, E-classes, which contain E-nodes. But all of our E-classes here, those are the dotted boxes, only contain a single E-node. Right, so we're not really representing any equivalences yet. And we say that an E-class can represent a term when you can sort of follow the lines and find the term within those boxes. So this E-class containing the division E-node represents this program, A times 2 divided by 2. And so we're going to try to optimize this program down to A. And we're going to do that via rewriting. And we're going to start out with this sort of potentially troublesome rewrite, which if you were in a greedy rewriting system would sort of represent a locally good idea, it's a strength reduction, but globally bad idea because you're going to take a wrong turn here and sort of miss an opportunity to cancel out this multiplication and division. So the way we do that is we look for instances of the left-hand side, just like in rewriting, and we apply the right-hand side. But instead of replacing the multiplication node with our shift, we add it to the same E-class. All right, now we've got something interesting going. We have an E-class that represents two terms. It's got two E-nodes in it. So we have our left-hand side of the rewrite, A times 2, and the right-hand side, A shift 1. And this notion propagates upwards. All right, so the E-class containing the division E-node, it's a singleton. There's only a single E-node in there, but it represents two programs. A times 2 divided by 2, that was our input, and now our misoptimized input as well. And long story short, this is a monotonic process, right? So I haven't lost anything. I can still see my A times 2 there. And so if I wanted to now go down the correct path and actually find the cancellation, I could still do that, despite the fact that I sort of took a wrong turn at the beginning. And in fact, you can hit a phenomenon called saturation here, where if we keep applying these rewrites, we'll observe that nothing actually happens to this E-graph. It's what's called saturated. You'll try to apply a rewrite, and you'll add the shift node, and you'll be like, hey, the shift node is already here, right? And when you hit this point, you've sort of learned everything that you're going to learn with respect to these transformations on your given set of data. And then finally, if we want to use this for optimization, the final step is called extraction. So what we do is we identify, well, where did we put our input? There's a lot of these different classes of equivalent programs, so we've got to remember where we sort of put our input, and so we put it in this funny shaped E-class here. And then all we do is we look for the smallest or cheapest, depends on what your cost function is, program. And if your cost function is sort of cooperative, we can do this very quickly via dynamic programming. And if it's uncooperative, then, well, we have to resort to sort of heavier techniques. So this is, again, the sort of whirlwind tour through equality saturation. The basic workflow is we take our initial program, We chuck it into the E-graph, and that's going to initially look like our boring E-graph, right? It looks like an AST, one node per class. And then we start cranking our rewrites. And again, this is a monotonic process, so you don't really have to worry about taking wrong turns. You can apply a transformation, and the things that were transformed are going to still be present within that E-graph. And ideally, you would hit saturation, but in practice, this is a non-terminating procedure for many rewriting systems. It depends on the system. You stop after some limitations, and then you can extract an optimized term, and voila, that's how you do optimization using E-graphs. This loop is hiding a lot of work here. This is sort of the bread and butter of the algorithm. This is where all the work is being done, and like a lot of sort of iterative search-based algorithms that are doing all this complex matching, there are some bottlenecks. Okay. And in particular, in our workload, the bottleneck is in a stage of the algorithm called E-matching. That's basically when you're doing the rewriting, you're looking for instances of the left-hand side. It's a lot more complicated in an E-graph because it's a compact encoding of a bunch, like exponential number of terms. And so you can get a lot of matches, and you want to filter out a lot of those potential matches that are not going to match the rest of your pattern. And so we developed a technique called relational equality saturation to sort of optimize this E-matching procedure. And this came from a couple insights. First of all, equality saturation, as I was saying, is a monotonic procedure. You can sort of squint and be like, hey, this is sort of looks like a database that is growing. We're just adding facts to it. We're adding more equations. We're adding more terms. It's only growing. We never lose anything. There's no destructive rewrites. And as I was saying, E-matching is the bottleneck. And if we sort of squint and think about, well, what is E-matching doing? Well, it's a backtracking search for substitutions that satisfy some sort of pattern. This is basically a formula. And if you're familiar with data log, which is I'm sure many of the folks in the room are, then these sort of terms, bells should start going off in your head. Hey, it's a monotonic process. We've got this whole search for substitutions that we instantiate on the right-hand side to add more things to the database. And so we started thinking, hey, can we encode equality saturation into data log? The biggest step of doing this would be encoding E-matching as a conjunctive query, as a relational join, basically. So let's see how we do this. The essence of it starts from a very simple flattening. This is the very standard if you want to represent tree structured data in a relational context. So here's a simple AST here, and we have one table per kind of function symbol. So you're going to have a plus table, maybe a minus table, F table, G table, times table, whatever. And the first couple columns are going to be the arguments of this operator, and the final one is going to be the value. And this is just a marker, sort of that is unique for every invocation of the function. So B plus C gives us BC, and A plus BC gives us ABC. These are just names for now. It's also worth noting that these constructors are they're functions, and so there's a functional dependency in all of these tables from the arguments to the output, and in fact in the other way as well for now. Okay. And this resulted in the tool, which is called egglog, based on egg, which is our original eGraph library, plus datalog. And when you really look at it, what it does is it boils down to datalog plus functions. So you need a notion of functional dependency, plus an extensible notion of equality. And we'll see how those two features interact in just a moment. Well, if you could click in this slide, you would see that these are links. But you can write programs that look and feel just like classic datalog programs. So if you wanted to do like your classic datalog program, you have paths and edges, and path is a recursive. Your edges are paths, and paths are edges plus paths. You can write that just as well in egglog. You can do some fun things by combining datalog with our extensible equality. And by extensible equality, what do I mean here? Well, in eGraph land, one of the primitive operations that you're allowed to do is say, hey, this E-class and this E-class are the same. We merged them, right? So we're saying that all the programs represented in this E-class and all the other ones in this E-class, we've learned that these are now equivalent. Okay? And in an egraph land, when you when you union these two E classes, this propagates up and you might learn new equivalences and things like that. Likewise, in egglog, everything reacts to these new equivalences. So if you wanted to write your reachability program, where you have a graph and you're talking about, what are all the paths through it, and then you just said, aha, this node and this node, they're the same, right? Well, in sort of graph land, what that would be like is you take these two nodes and you merge them, right? This is going to create all sorts of new paths. And that just sort of falls out from our egglog implementation. And finally, you can do things like equality saturation. You can represent tree structured data, and you can prove them to be equivalent, and you can extract out optimal things. And this implementation of equality saturation falls out from the interaction between functions and extensible equality. So let's briefly just take a look at where that comes from. All right, so if you have functions in your data log, you typically, or in any relational context, again, we're going to sort of tabularize them. So, it's a table, an n-ary function goes to an n+1-ary table, where the output is the last column. And so here are two tuples, right? They're recording that f of a is b and f of c is d. Easy peasy. Well, what happens? Our equality is extensible in this world, right? So what happens when the user asserts a equals c, right? We said that there's a functional dependency between the first column and the last column. And these equivalence assertions can violate. They can induce violations of functional dependencies. So what happens, right? And so the natural question is, what happens in, if you look at data logs that feature semi-rings or lattices, where the last argument has a lattice value? What happens when you have two tuples who overlap in their first n arguments? Well, you combine the last argument according to whatever the lattice laws or the semi-ring laws of that system dictate. Okay? And we have a very similar system in egglog. We call them merge expressions. So we can do the lattice stuff, and here's a very straightforward example of how that would work. So if you have a function foo, it just goes from integers to integers, and we need to give it a way to say, hey, if there's a collision in our inputs, how do we rectify that? What do we do between? We can only have one output. We have to pick one. So say we set foo of 7 to 5, and we set foo of 7 to 4. Well, here it's pretty clear. Our merge expression is going to take the min of the old and new values, right? So that's what's going to happen here. More interestingly, we can get basically congruence closure, which is the thing that powers the egraph, by just getting a little bit more creative with our merge expression here. So if we wanted to build terms, tree structured data, well, that's nothing but a constructor is just a function that takes in an expression and maybe a couple expressions and outputs an expression as well. And how do we rectify sort of FD violations there? Well, we use the underlying union function, right? And this is going to, in our union find, sort of in the underlying data structure that's tracking equational, the extensible equality, we're going to identify those two values. Okay, so all those extra features are really nice, but again, what I was saying earlier, the reason why we sort of dipped our toes in this relational technique is we wanted e-matching to go faster, and long story short, it goes way faster than the previous approaches, which just use backtracking search. We're sort of cheating here because it's asymptotically faster, right? These algorithms were never designed to search very complex patterns. You can, if you squint, you can sort of read this very long pattern, which translates to a reasonably long conjunctive query that has all sorts of variable reuse. And the backtracking algorithms just aren't built to scale for that. But the relational technique does. And for simple patterns, you don't gain very much because there's no joins. Okay, so what is actually the join algorithm that is powering egglog and other, and now hopefully some other relational techniques? And this is another strain of work called free join. And I promise you, you can. This paper was just selected as a SIGMOD research highlight, and my colleague Remy did a great job of sort of simplifying the exposition and making it much more readable than whatever I'm about to throw at you in the next 2 minutes. So I encourage you to check that out. The basic idea is you want to combine some of these newer worst case optimal join, also referred to as variable at a time join algorithms, with binary or relation at a time join algorithms. We want to sort of break that dichotomy in free join. And as a teaser, I'm going to explain how free join works, but one thing that I'm not going to explain is how do you compile these plans? I think this is an open question that I would love to see some sort of future work on. So let's start from binary join, and we'll get to free join, and then we'll approach it from another perspective. This is the Clover query. If you're not familiar with it, it's basically x joined with 3 other things. And let's just look at the free join plan, and we'll explain what it means. So this is a free join plan that sort of represents the binary join plan, where you first join R and S, and then you join the result with T. So if we're going to do that with nested loops, what would we do? Well, we would first iterate over R. And for every tuple in R, and so that's sort of what we're doing here, each of these groups, each line corresponds to a loop level. And the first atom, or subatom rather, tells us what we're iterating over. Okay, so we're iterating over R, and we're taking both values, x and a. And then to the right of the bar, that's going to tell us what we're looking up at this loop level. These are the sort of the probes. We're probing into those hash tables. So we're going to look up using the join key for the R and S join. We're going to look up into S. Well, that could result in many values of B, so we're going to loop over those, and we're going to probe into T. And then finally, there could be many results in C, so we in the C values of T, and we're going to loop over those, and we yield. There's a better plan, though. There's a pretty straightforward optimization to this, and that's you can see that this indexing into T with value x, there's no need to wait to the second loop level to do that, right? As soon as x is bound, you can do that right away. So the free join allows you to very concisely represent these kind of optimizations. You could go even further and say, hey, this value of a, we don't need to iterate over all the attributes of R. We only need to iterate over the x values. We don't need a until much later. And so now we could write at the first loop level, we're going to iterate over just R of x, and we're going to look up x and t. And then, sorry, these are 3 separate loop levels here. I just ran out of space. But you'll notice I didn't write a bar here. I just wrote a comma. And that's because, well, when the schema of all these subatoms is the same, you can sort of choose it doesn't matter which one you iterate over. And in fact, you want to choose dynamically to say, hey, I may not want to iterate over R and look up at S and T. I may want to iterate over S instead. And this represents a sort of an intersection that you might see in generic join, where you're dynamically, based at runtime, choosing whichever one of these has the lower cardinality to do an intersection in the time scaling with the minimum of them. Okay. And I think this will be even more clear when we approach free join from the generic join side of things. So let's look at the triangle query. If you're familiar with worst case optimal joins and how generic join operates, the free join plan for this isn't super surprising, right? You're going to intersect on all occurrences of x, loop over them, intersect on all occurrences of y, loop over them, and then intersect on all occurrences of z and loop over them. Okay? But this is free join. So if we wanted to do a different plan, we can. We can represent all kinds of different plans. Like say, for example, we didn't have a try to index over R. Or maybe R is huge and we didn't want to build such an index. We wanted to scan over it. Well, we can scan over it. We can loop over x and y and then do immediately lookups into S and T. And then we can still intersect over z in the second loop level. So we've lost a loop level. So for some statistics, this might be a better plan. And that's basically all I have to say about free join. You should check it out. We have an efficient implementation, blah, 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 in the paper. There's some cool systems things. We have an eval against DuckDB. Again, we don't know how to generate these plans. So we started with binary join plans from DuckDB and sort of massaged them into free join plans and did some light examples. But you could probably, from scratch, come up with much better plans. Not only is it faster than DuckDB, but one interesting thing that we noticed, and other folks have noticed this as well, that these join plans that are based on worst case optimal join are much more robust to bad statistics. If you have bad statistics, this might be an algorithm to check out. OK, that's all I got. Thanks.
So a Jeffrey, do you want to set up? So we have time for one question, perhaps.
Thanks